Okay, so we're going to work on another example, part 3 of trig identities. Okay, I've already set it up a little bit. The right side here is 1, so that's very simple. Okay, the left side we have some potential for simplification. First of all, we have a 1 minus cos x and a 1 plus cos x, which does suggest a difference of squares, so I'm going to expand that out. And again, we have no brackets over here, so I'm definitely going to want to expand this out or do something with these brackets so they can simplify. In this case, 1 times 1 is 1. Cos x times negative cos x times positive cos x is negative cos x, negative cos squared x. And then a negative cos x and a positive cos x just adds out. Or I notice it as perfect square, plus minus, difference of squares. And then I'm left with 1 plus cotangent squared x as well. Okay? Now, 1 minus cos squared x, if you see the squared, you're going to think, okay, there's my Pythagorean identity, which means that's going to be sine squared x. Now I've got a 1 plus cotangent x, and I'm going to use my cotangent definition as cos over sine. So it's going to be sine squared x as 1 plus cos x, cotangent squared x, cos squared x over sine squared x. Okay, sine squared x, and then I'm going to go, okay, well, let's collect like terms. So this is going to be sine squared x over 1 times sine squared x, multiplying the top of 1 over 1 and the bottom of 1 over 1 by sine squared x. Now we have a common denominator, cos squared x over sine squared x. Then I've got sine squared x, leave that alone. And I've got sine squared x plus cos squared x all over sine squared x. Now what's interesting is this sine squared x and this sine squared x come out, and sine squared x plus cos squared x is going to be the Pythagorean identity, which is a 1 over a 1, which is a 1. And so left side is equal to right side. And since that's the case, therefore, it has been proven. So again, kind of a slick sort of idea or turn of events, that being the case. Okay, I'm going to leave this one for now. Okay, depending on the amount of space I have in my phone. So I'm going to go ahead and do this one. And the reason why I'm going to go do this one is because you've got the varying powers of sine. You've got the sine ratio of beta, sine squared beta, sine of beta, and then a constant. So this is a really good, clear, we'll make the right side equal to sine beta minus 2 over sine beta plus 1. Okay, but the left side we're going to leave as this. Now, what I'm going to do before I'll write it out. Sine squared beta minus 3 sine beta plus 2 all over sine squared beta minus 1 is what I'm going to do is I'm going to say, okay, I'm going to let sine beta be equal to a. What that's going to do is it's going to make it a little bit, so that's going to be a squared, and that's going to be a squared, because sine squared beta and sine squared beta, if a is sine beta, then a squared is sine squared beta. And then minus 3, and this sine beta is a, so 3a, and then plus 2. And that's just minus 1. And what you're going to see is it's an easily factored, well, multiplies to give positive 2 and adds to give negative 3, a minus 2, a minus 1. And this, of course, is a minus 1, a difference of squares, a plus 1. Okay, the a minus 1's come out, and of course our a value cannot equal 1. Okay, which means sine of b cannot equal 1 in this situation. All right, but more specifically, what I do is I get a minus 2 all over a plus 1. Well, if I go back and I put sine of beta back in, sine of beta minus 2 over sine of beta plus 1, I create this scenario where it's equal to the right side. Okay, and so I got left side is equal to right side. Since that's the case, therefore it has been proven. Okay, now I'm going to see if I have enough room to take one more. I'm really